colleagues, dear guests, good morning everybody. On behalf of the Faculty of Informatics, a warm welcome to our event, A Paradigm Shift in Computer Science, ? So my name is Stefan Woltran, I'm professor here at TU Wien for Formal Foundations of Artificial Intelligence, and together with Lynda Hagedorn and Hannes Werthner, we planned this event. We have put together a program which we believe will address this question from different angles, with the overall goal to understand the impact of AI today to informatics, but to science in general. Our faculty, which celebrates its 20th anniversary this year, has already witnessed several drastic changes. So just take the rise of the internet, which had huge impact on the way we thought about privacy, security, human-computer interaction, the way students learn how to code, or the way we have to teach. Just think about virtual classrooms, Zoom sessions, and so on and so forth. But what we see today, I think there are two main things to consider. The one way is that AI is nowadays applicable, available for everybody on the one hand, and on the other hand, computers are now understood as tools which deliver results without 100% certainty, with probability, with possibility. And that's also changes the way computers are received ultimately by society. So what has triggered me and us to organize this event is that we believe that computer science as a discipline is somehow, to some extent, ignorant about being a research object itself. So we asked ourselves several questions. What do the current developments in terms of AI mean from a philosophy of science point of view? Have we seen a similar situation in the history of computing as we see today? Or is it just everything is just a big hype without any effect? So these are the questions we would like to discuss in the next days, and Hannes will say a few more words about the actual program we have planned. What remains for me is to mention that this event has been organized in cooperation with two FWF clusters of excellence, the one on bilateral AI and the one on knowledge in crisis. And we will have distinguished speakers from both of these clusters. I would also thank the Center of Artificial Intelligence and Machine Learning and the Center for Computer Science for their support in organizing this event. But last but not least, a big thanks goes to IWM. So we organized this event together, and therefore I hand over to Lynda Hagedorn. Thank you.
Thanks. Good morning to all of you. Very warm welcome to you also on behalf of IWM. In German we have the complicated name Institut für die Wissenschaften von Menschen. In English it's Institute for Human Sciences, which is by the way not a very exact translation, but Institute for Human Sciences, and we are for 3 years now working also in the field of digital humanism together with our colleagues from TU. We are very happy and very grateful to our colleagues from TU that we have this project and that we are doing this together. And since our institute already has the human in its name, I think it's quite fitting that we are working also contributing to the field of digital humanism. Just let me mention that our program is supported by a ministry, an Austrian federal ministry with a very long name. I will save you the name. I will call it the Ministry for Climate Action and many other things. Innovation and technology is also one of them, and we are grateful for this support. And the main thing to say about our program, our fellowship program that we are doing together with the TU Wien and IWM, and very much by the initiative of Hannes Werthner, Werthner, I have to say a few words on this program. We invite 2 fellows per year to come to Vienna and to work in the field of digital humanism. The current fellow is just here in front, Thomas Haigh. He's the current visiting fellow of IWM and TU. For him, we are with him together. We have organized this conference today. And actually 2 other fellows are also in the room. We have a former fellow, Viola Schiaffonati, who is here, who was our fellow this spring. And we have a future fellow of whom I don't, yeah, he's here. Hans Ackermans is also here. He will be our fellow next year. So you see, there is something coming together, people, networks. And yeah, I will say. And not to forget, I would not have forgotten, but Hannes reminded me very friendly. This program also entails the invitation of junior fellows. And those who are currently at the IWM are also in the room. We are very happy that they are joining for this conference. Francesco Striano, I don't see him now. Yeah, he's here. And Li Yi, who is here in the front, are also currently our visiting fellows. And it's a great thing that we can do this and that we can bring people, spread the news about this program. We have already very many good applications for the juniors program, but spread the news. I think it's worth it. Hannes Werthner, to continue.
Thank you. Thank you all for coming, and I'm really happy to see you all here. Helga reminded me that it started here 5 years ago. We had the workshop on digital humanism, where several of you joined. We had the Vienna Manifesto, and also this workshop is somehow a result of our initiative coming out of this cooperation, but also from the, let's say, the scientific point of view we did. And there is one big landmark we have reached, our 2 books which are open access downloadable. One is called Perspective on Digital Humanism, the other one is called Introduction. Together they have already over 1 million downloads. When we celebrated the 1 million, now we are at with 1,080,000 already, over 80,000. So it's a real, I think it's something which is part of the international scientific community. Very short to the program, you have seen the program. We are starting with the history of AI, then we look at the 2 different, let's say, for me, defining issues of AI, which are the basic methods. We look at logic and we look at machine learning and statistic, but not for an explanation, but also to see what they can and what they cannot do, okay? Then we have a presentation on the 2 paradigms, could they coexist or could they be combined or not? Then we have something on paradigm and new paradigms in computer science. We have one on, let's say, AI in other sciences. We have one view from philosophy, looking at knowledge, AI, and what can philosophy tell us. And at the end, we have something on the institutional part. What does this mean for an institution like a university? And there we have a final presentation. It's organized in slots of 1.5 hours. So if you have to go out, please wait this 1.5 hours, because the room is a little bit small and it might be hard to get out. It's organized that we have a presentation by 35 minutes by a keynote speaker. Then we have a panel with 2 panelists, which are in essence respondents. Each of them 10 minutes we have chosen, and then we have overall discussion. We have chosen this format to be more interactive, to have more room for open discussion and participation. You are offered 4 coffee breaks outside, 2 lunch. You don't even have to pay for the lunch. It's on the room just go out and straight on. It's in the Hörsaal Zemanek. There are wardrobes all around, so if you have a problem with your coats, you can do that. What else do I have to say? We will take minutes. So we have students, colleagues of us, who will somehow make summaries of each session. And as a speaker or respondent, you may be approached by them after your session if they need something for clarification. It should be at the end, we would like to have a summary of these 2 days. We don't know yet how this will be published or how we will communicate this to the outside, but we wanted somehow to have a summary of what was discussed and the major outcomes. And I already thank now those who have volunteered to do that and to write these minutes. Final thank goes to you, Stefan and Ludger. Both of you, because it makes fun to work with you, because we sit together, and we always do it in the Viennese coffee house tradition. We meet in coffee houses, and then we discuss the program.
Very early in the morning.
Very early in the morning. So, but it's always, we had, I think, 4 meetings, and then it was done, the program. Okay, so I really want to thank you. And with this, I think I have nothing forgotten. I thank you both for the opening and for cooperation and real support. I would like to go over to Tom, who is the current senior fellow of the Digital Humanism Fellowship Program at EVM, joined together with the Faculty of Computer Science here at the TU Wien. Just a very short note. He is both trained computer scientist, studied at the University of Manchester, and he is also a historian. So he has both flavors to speak about the history of AI. He has written several textbooks and articles which won awards. He is regularly publishing in the communication of the ACM. He's even running a lab where he is redoing calculation using the old computers. So really, really looking at what the results are. And he's currently working on a textbook on AI and a concise history of AI, which is the issue of your next book. And he had 35 minutes to tell us something about the history of AI.
Yes.
And everything. No, final remark. When you afterwards have a comment or have a question, you get a mic, so because we are streamed. And before you start your question, please say who you are so we know this one. The floor is yours, Tom. Thanks for coming.
Thank you. I'm glad to be here, and I've had a nice time in Vienna this month. I've also been teaching a course based around my draft book here at the Technical University, which has been an interesting experience, and I've already got a lot of notes on how to improve it before it's published. So yeah, I was assigned this title, The History of AI. I've got a different talk which I gave at the conference last year, and I gave at the IWM last week, that has titles like Artificial Intelligence, the History of a Brand, or Artificial Intelligence, the Brand That Wouldn't Die. The title for the short book is going to be something like Artificial Intelligence, the History of a Brand. So that is the framing concept here. And I'm going to say a little bit about the brandness of AI at the end. But in this talk, in the context of the workshop, I'm going to focus more on the historical relationship between old school, symbolic 20th century AI and the development of computer science. All right, this should click. Anyone? Am I pushing the right? It's that one, is it? On the side? No, it's just turned off. Okay, now it lit up. That's promising. The down goes forwards. Interesting. So I'm also here, in a sense, at the start of the workshop, as well as giving my own talk. So I just thought to review the promise that has been made and see how I can contribute to that. That we will be looking at a possible paradigm shift in computer science, the move from logic and algorithmic certainty to probability and LLMs as story machines. So there's a couple of things I have to pull out. One of them is this idea of a paradigm shift and what that even means. I'm going to talk very briefly about that. The other is the idea that somehow what we're seeing right now with generative AI and ChatGPT and so on represents some kind of fundamental potential new model for computer science. So in the history of computing, there's a book. It's not the kind of book that a professional historian would write. It's the kind of book that a mathematical logician would write. But it's making the case that computing is fundamentally logic, that the invention of the computer was mostly the matter of having some kind of conceptual idea about Turing machines and so on, and that the engineering stuff is not really that important. But that's certainly a kind of classic logic-oriented way of seeing the world. And I think that's a conception of computers as engines of logic that a lot of computer scientists would agree with. one of the ideas that I and a number of other people coming from humanities traditions are invoking in the context of generative AI and ChatGPT is the concept of bullshit. So this is from a book that made, surprisingly late in his career, Harry Frankfurt into a bestseller. It also gets invoked a lot in the concept of in the context of fake news, and particularly in the context of Donald Trump. So the idea is that there is a difference between a liar and a bullshitter. So a liar knows what the truth is and is strategically, for some reason, choosing to disregard it and convince you of something else. Whereas a bullshitter just gets up and says stuff, and they don't even know themselves whether it's true or not. That is a very good description of generative AI and ChatGPT, right? The idea that mostly it works and then sometimes it hallucinates is really, at best, a euphemism, right? It just makes up stuff that statistically resembles what's in the training data, and sometimes it's true and sometimes it isn't, but there's no, unlike what 20th century AI was trying to do, there's no concept of facts. So if I was titling the conference, I might have gone with From Engines of Logic to Engines of Bullshit, question mark, as another way of thinking about that possible shift. The other obvious question is, oh, a new paradigm for computer science. So what was the old one? And in some ways, that's the question that I'm going to try and answer in the talk. I don't think you can say there was a single paradigm for computer science, but I found, thinking through these questions for the workshop, that thinking about what did classical AI and computer science have in common during this vital period in the 50s, 60s, when both disciplines were coming into existence, helps us get a sense of what the intellectual core, in as much as there was one, of computer science might have been. So, of course, the concept of paradigm comes from Thomas Kuhn's book, The Structure of Scientific Revolutions, which, like on Bullshit, was a surprise bestseller. In this case, I think back in the 1960s. And I came across this actually in one of the few courses that I was able to take outside the computer science department as an undergraduate student. I did a philosophy of science course, then I did another one. And I was also really excited when I read it. It's a classic book. It's provocative. It's also something that since the 80s has been rather unfashionable with historians of science, and I suspect also with philosophers of science, but we don't really talk to them anymore. And so the idea there is essentially that scientific change is discontinuous and it's fundamentally a social process of changing people's minds, but that people don't really change their minds. The adherence of the old paradigm will just die off and be replaced by new ones. So it's an idea of kind of discontinuous change, revolutions in science around the paradigm. Kuhn was famously criticized for using the term paradigm in some giant number of ways. I can't remember how many, 19 maybe, like definitely more than a dozen. Someone counted them and was like, hey, this is incoherent. Why do you use the same word for so many things? In the second edition, he tried to fix that, but it didn't really work. So the revolution part actually is something I think that science studies scholars would say doesn't map very well outside his own specific case studies. But there's also the idea of the paradigm. So that's the idea that some specific tangible scientific accomplishment, like, say, Newton and the laws of motion, in the beginning is a bit underdeveloped, etc., but it has enormous potential in certain cases, and then people spend decades, or I guess in that case, hundreds of years, extending it, improving it, applying it to new things, etc. And then eventually the old paradigm runs out of steam because it's coming up against problems that it can't cope with anymore, and then it's time for some radical new thing, right? If any of you have read the book, The Innovator's Dilemma, in some way it's the same. It's the same kind of idea there, right? That the entrenched company is really good at doing the old thing. Then you reach a point where what you need is a startup that is disruptive, right? Disruptive innovation, it's all Silicon Valley talks about. In some ways, it's the same idea. That there's going to be a disruptive, underdeveloped new idea comes along that is just so good at doing new and different things that it's better adapted for the current situation and it sweeps away the old one. So that's the idea of the paradigm shift. The part of Kuhn that actually I think most of us would find more useful at this point is this idea of normal science, of what happens between the paradigm shifts. So in this study, for example, Kuhn says, like, look at the way that students learn in science. They don't learn by going back and reading history and seeing the original sources. They wouldn't be familiar with the notation or the way ideas were originally expressed. They get everything filtered through textbooks. And so one of the things I looked at in this is AI textbooks and how they reflect the adoption of a definition of what artificial intelligence is. The other thing that I think is kind of provocative to think about there, and often gets overlooked, is that according to Kuhn, the core sense of paradigm, which he actually took from grammar of all things, is the idea of an initial tangible example. So he didn't think so much in terms of abstract theory, he thought in terms of an accomplishment that uses some kind of new scientific method to solve a problem in a way that makes people say, whoa, you know, how does that work? I want to do something like that. And then they try and copy it. So it's the kind of tangible accomplishment. So that's also something that I pay attention to in the study. In a talk like this, you can only say so much and you can't try and put too much in. Fortunately, if you are interested in learning a bit more, you don't have to wait for the book because I'm publishing a 5-part series in Communications of the ACM, the first 4 parts of which are now published and it's freely available online even if you don't have a subscription. I'm going to be drawing in this talk mostly from these first 2, conjoined twins, AI and the invention of computer science, and this one. And by the way, there was no first AI winter in the 70s, right? Don't believe that. I'd be happy to talk more about that to anyone who's interested. Then the other parts deal with the AI boom in the 80s, what happens with AI in the 90s, which I argue is a period of intellectual pluralism. And if CACM is going to let me, we're going to get way more clicks if we entitle the last part Engines of Bullshit. But I may have to call it AI Then and Now to reflect their delicate sensibilities. All right, so main part of the talk here, right? Why are computer science and AI centered on algorithmic certainty in the first place? So you've probably all heard of the Dartmouth Summer Research Project, 1956. The AI brand was invented in a funding proposal to the Rockefeller Foundation asking for money. And it was mildly successful. They got half the money they asked for. It was a deliberate choice of artificial intelligence as a new brand versus cybernetics, which was an established one. This wasn't the first time anyone suggested a computer could think. One of the arguments I make is actually, in the cybernetics viewpoint, computers were thinking already. In the AI viewpoint, computers would only be thinking if they could do certain specific hard-to-program things. But one of the reasons it's so remembered is that the 20 people who attended included 2 of the 4 organizers, John McCarthy and Marvin Minsky. They also included Herb Simon and Alan Newell. Those 4 men are remembered today as the founders of artificial intelligence, and they all went on to win Turing Awards and to establish the most important centers for AI research. So that's the conventional origins. Now, if we look at the proposal, which is freely available online, it's kind of interesting to see what they conceived AI as being at the beginning. So in some ways, some of these things are quite familiar. We've got neuron nets there, number 3. We've got self-improvement, which essentially is learning, randomness and creativity. There's also abstractions. Of course, the idea of layered abstractions is one of the defining pieces of the self-conception of what computer science is about. They're also, though, thinking about the machine defining its own abstractions. So that's also there in a machine learning kind of way. Natural language, number 2. And then a couple that seem like outliers at this point. Automatic computers, a machine can do a job, an automatic calculator can be programmed to simulate the machine. That is essentially the universal Turing machine kind of concept. And theory of the size of a calculation, which of course is an important part of computer science, right? Algorithmic complexity. We don't think of that as being part of AI now. So I was interested to see at the beginning that kind of cluster of ideas, all of which you've got to give it to them, are indeed important things to look at, right? They've got a pretty good sense there of some things that are going to be extremely important as computer science develops. But there's also some kind of degree of arbitrariness there. And one of my larger arguments is that what gets branded as AI or not as AI is always kind of arbitrary, that it has more to do with who is funding it or what kind of group it's developed in than it does to do with necessarily any particular connection to cognition, right? It's maybe hard at this point to see why they thought computational complexity was AI, but some of those things, if it had gone another way, we might think it's perfectly natural, right? I mean, there's a famous story that computer vision became part of AI when MIT decided to have a student work on it for a summer. And ever since, if you work on computer vision, that typically has been connected to an AI kind of identity. All right, so institutionalizing AI. People pay a lot of attention to the summer school. It was not actually seen at the time as being enormously successful, right? What really matters is not what happened that summer, but what happens over the next 5 years or so. And what happens is that people are able to take this new brand of AI and institutionalize it to get money for it and to set up research groups in some extremely important universities. So the first 3 centers for AI research in the US are MIT, where Minsky and McCarthy, both are by 1958. The description that historians like to quote is that they start out with 2 programmers, a secretary, a typewriting machine, and 6 graduate students. And that is the beginning of artificial intelligence as an institutional field. McCarthy quite soon leaves and goes to Stanford, where in 1962 he's able to set up an AI project. That develops into the Stanford AI Lab, a famous, now demolished wooden building out there in the hills above campus. And that is developed in 1965, the same year that Stanford founds its computer science department. MIT doesn't exactly have a computer science department because of MIT weirdness, but it's got some labs and some programs. And AI is an enormously prominent part of Project Mac and the developments that make AI a leading, that make MIT a leading center. Newell and Simon are there at Carnegie Mellon, which is in general a lower tier institution substantially at this point. Their work with artificial intelligence is a key part of the founding of the computer science department there in 1965 and the rise of Carnegie Mellon in the institutional league table. It's also important that particularly those 2 institutions, MIT and Stanford, are real outliers at this point in pioneering more generally a new model of the university. So they are receiving far more federal money for research and also for development projects to actually build technologies for the military, particularly in the case of MIT, than any other universities. So they have access to funds in a way that other centers don't. MIT is always expensive. It fits very well with this kind of emerging Cold War mindset. So in the article and in the book, I talk a bit more about the context of this within the Cold War and within the context of the availability of funding. So I don't think it's a coincidence that it's MIT and Stanford in particular where this develops. So the National Science Foundation isn't funding computer science until the 70s in itself. It's funding universities to buy computers, but it won't fund something that is called research in computer science because computer science doesn't exist yet and there's no directorate for it. So the money is coming from the ARPA, right? You've probably heard of the ARPANET, but ARPA is really important also in funding developments in time sharing, artificial intelligence, and graphics during this period, and it's the most important funder, and it's got a very cozy relationship with MIT in particular. I talk about that in the article. So the point is, it's not that computer science exists and AI comes into it. The 2 fields are basically coming to existence at the same time, in the same places, with the same people. And the first computer science PhD graduates in 1968, the Turing Awards beginning, I think, 1966, the first degree programs a few years earlier, etc. So AI develops as a subfield of what I think of as this federated discipline of computer science. And just an interesting thing, if you Google various league tables, you pretty much always get the same results when people try and do world rankings, US rankings in computer science. It's pretty much still MIT, Stanford, and Carnegie Mellon coming out on top. I'm not saying that they did that because they were the three key institutions for AI through the entire 20th century. But I don't think it hurt either. I think AI was an important part of establishing them as the elite global computer science institutions. So the AI agenda from the 60s to the 80s, I'm going to talk about this a little bit, then I'm going to talk a little bit about computer science more generally and what the connections were. They defined intelligence really as things that computers couldn't do, also as things that the humans that they personally viewed as being very smart were good at doing, like playing chess, for example. People have certainly looked at the cultural dimensions and the assumptions and that kind of definition of intelligence. And of course, famously, the things that people thought were hard turned out to be easy and vice versa, right? They're improving in chess turned out to be not nearly as challenging as playing ping pong or, you know, navigating through a room without bumping into things. The symbolic approach very definitely and deliberately wins out over neural networks during the 1960s. So the core idea of AI, which is really coming from Newell and Simon, is that computers manipulate symbols representing knowledge of the world according to algorithmic rules. They would call it heuristic. They would say heuristic is not algorithmic at all, etc. But, you know, I'm not really convinced. And they would say that search is the core technique. And one of the things I quote in the book is, I found some lecture notes from Oxford University in the year 2000. It was for the introductory lecture to AI. And it finishes with, everything in AI comes down to knowledge representation and search. So that remains the way the people in the system see it. They're initially looking more for general purpose reasoning mechanisms. By the 70s, they're thinking much more about structured knowledge representations. But with some shifting of emphasis between them, everything in AI in this era is search and knowledge representation all the way down. They also start out with the idea that there are going to be these general purpose reasoning mechanisms that work across tasks that can be discovered. So that's why they pick chess. They think if we can make a machine that can play chess really well, it's going to be able to reason and do all these like other things. That is, as you all know, I think, is not how the problem of computer chess was actually solved. So by the time computers are world chess champions, there's also no particular belief that has anything much to do with human cognition. That happens in one way or another in a lot of AI. They start out with some idea of the brain must work this way, or this is connected with cognition. And then once you go down to the level of this kind of normal science and grinding out improved results, you've got people making optimization algorithms that honestly, on a mathematical level, I don't believe are clearly distinct from what's happening in operations research. But you know, for essentially these historical and cultural reasons, some things get branded as AI, some things get branded as OR, some things just get branded as algorithms. I've got some examples of that in the papers. So that is 20th century AI summed up in a rather concise way. You've also got the idea there that as everything's about symbol processing, it's also about rewriting symbols, which has got some resonance with broader ideas in computer science. And you've got the specific idea too. The culture of AI from the beginning is about make a working system that demonstrates this thing that you're talking about. So the path to get ahead as AI is always, as a PhD student, to go to Stanford, Carnegie Mellon, or MIT, to work with the famous professors, and to produce, as your dissertation, a system that appears to show some progress on a trivially small problem for some kind of exciting new method. If you do really well, it's going to be written into the AI textbooks. All right, back to computer science. So where is CS coming from? Well, in the 50s, universities have computers. Some universities have built their own computers, which obviously requires electrical engineering talent. So they probably have computing people in electrical engineering departments. Other universities are just buying them from IBM or other producers. They have computer centers. There are specialists in the computer centers to help the physicists and the economists and the other real scientists get their problems programmed and run. And those people develop an interest in things like systems programming. What there isn't in the 50s is a computer science department. So those computing people from both sides basically say, wouldn't it be nice if we could justify what we're doing in terms of understanding computers better being an object of research in its own right, and not just something that we do to help the real scientists do their work. And that essentially is where computer science comes from. They managed to persuade administrators to let them set up programs, etc. So to keep that going and justify themselves, they need a body of theory of their own. So early on, for example, numerical analysis is really, really important because they mostly do numerical calculations. But the mathematicians already have numerical analysis. Plus, it's kind of a low-status piece of mathematics. So that's not going to cut it as the central thing in this new discipline. The same with electronic engineering and the hardware stuff. That field already exists. Information theory is something that people get a bit excited about at the beginning, and its connection to automata, although that already is established in communication engineering. Programming languages and compilers, big early center, etc. But I have a sense that broadly, they're looking around for some piece of high-status mathematical distinct theory that other disciplines don't already have. And my argument is that early on, to some extent, it seems like computer science is looking to AI to fulfill that role. Now, I should also say here, this is challenging to do because the history of computer science basically has not been written. So the most downloaded piece I ever did, it went reasonably viral because of the title, Tears of Donald Knuth in CACM, got 120-something thousand downloads. And if I called it Reflections on Internalism and Externalism in the History of Computing, it would have got 15 downloads. But everyone wants to know why Donald Knuth was crying, right? Because he's such a beloved figure. Turned out he was crying because historians had made him sad, because we'd stopped doing technical history and we were writing like social history and so on. And what I said in response is, nobody in the entire history of computer science in the US has been employed in a computer science department to do history. So it's not surprising that historians aren't writing the kind of history that computer scientists would like, basically, and find useful in terms of doing computer science better. Historians are employed in history departments and media studies programs and so on. And so they're doing the kind of history that is going to get them tenure there and make people interested and is legible to people who don't particularly understand computer science. And so a result of that is no one has been particularly interested in writing a book that tries to tell the overall history of computer science. There aren't really conferences on the history of computer science. So the task of connecting the history of AI to the history of computer science is more challenging because the history of computer science has essentially not been written. But if you just look at something basic, so one of the things I do for ACM, as well as write the columns, is I edit the Turing Award website. So I write or commission profiles of the new winners. I've been reorganizing the research categories. I've made video clips for them and so on. So this is just some information I had to hand. And if we look at the winners of the first 10 Turing Awards, which is 11 people, 4 of the first 11 people to get a Turing Award, right, which is one of the first things ACM does. So to start out with, it's not $1 million, it's $1,000, but you do get a nice silver bowl and you do a lecture. And clearly, computer science is looking around and saying, well, what do other disciplines have? They have prizes, then they have lectures. We need one of those. This is a part of our discipline building project. And if you look at the areas that people are winning in, okay, so Maurice Wilks builds a computer, Hamming is information theory, plus the first chair of the ACM, Wilkinson is numerical analysis, Dijkstra is a lot of things, but I think at this point, particularly operating systems and compilers and algorithms. Bachman doesn't even have a PhD, but he does invent the database management system, so he won it the same kind of way that, say, Tim Berners-Lee does later on, just for doing something that's really important, even though he's not really a computer scientist. And Donald Knuth, but, 4 out of 11, artificial intelligence. So if you go by that, you say, like, what is the discipline putting forward as its intellectual high ground with these prizes? I think you can make a plausible argument that it is trying to use AI in that context. And just a general point as well, I don't think computer science has a paradigm. Computer science develops in what seems to me an unusually federated way, in that there's a kind of small central authority, an overarching discipline of computing that maybe some more elite kind of figures identify with. But it seems like even from the 60s, with the growth of interest groups, conferences, journals, and so on, you could say database management systems has got a paradigm, right? COD, relational stuff. Communication, yeah, it's kind of got a paradigm. It goes with packet switching and the OSI 7-layer model. You can find plausible paradigms in these specific areas of computer science. In some senses, the question of if computer science has an overall paradigm is related to efforts to figure out which of these pieces is the highest status and most underlying piece. What they finish up with there is, of course, theoretical computer science. Although, is it really the paradigm for everything? I don't know. You're the computer scientists. You tell me. But it doesn't seem like particularly less elite researchers are always identifying as strongly with this as the underlying thing. But what we see is from 75 to 94, in contrast, there are no AI winners. And there are a lot of awards around algorithm, classification, finite automata, and basically computability and computational complexity are dominating it. So if we give, if we say like at half time, looked like AI was winning 4-0, unless you count Knuth, I'd say theoretical computer science has made a storming comeback to win 9-4 by 1994 in the second half. And that, I think, rather than AI, fulfills that kind of role of the intellectual high ground of computer science. But of course, the thing to understand with this history of computer science is there's no PhDs in computer science until 1968. There are computer science programs from the early 60s. By definition, nobody involved in computer science until 1968 at the very earliest has got a PhD in computer science. In a sense, like everybody is an intellectual migrant from an established discipline. So they've got to try and pull together these ideas that early faculty are coming with from different things. I think early on this even plays out differently in different programs. The main centers come up with their own distinct concepts of what computer science is that later get more homogenized. So the late Mike Mahoney of Princeton University, so I edited, for years he was supposed to be writing a book about the history of theoretical computer science, and he never did. He wrote some articles instead, I think. He was actually a student of Kuhn, as it happened. And I think he struggled with the project for various reasons. So he produced a series of dense and provocative articles that also included these visual depictions of what he saw the story of the assemblage of theoretical computer science from these other areas was. I collected them after his death in this book, Histories of Computing. I'm not going to talk through kind of everything you see here, but you do see the concept, right, that computer science is taking ideas from electrical engineering, coding, switching theory, mathematical logic, linguistics, neurophysiology, and it's exerting itself, and it's putting them together, right? Particularly here with the idea of the Chomsky hierarchy of grammars and its relationship to different classes of automata. So those pieces existed previously in different intellectual contexts. In assembling itself, computer science joined them together and made new things, kind of like Lego, basically, building something new from existing pieces, that then becomes the foundation for new work. So if computer science has a paradigm here, it's kind of assembled from the pieces of other stuff. It's also interesting in this other chart that he has for what's going on, right? So, we get here to Scott and Strachey and so on, some of those theoretical winners. But then up in the corner, he's also crediting McCarthy and Lisp with this important role of taking lambda calculus, turning it into a programming system, etc. So Mahoney was not interested specifically in the history of AI, but just in talking about the history of computer science. He found it necessary to bring in some of these AI accomplishments. I also make the argument that while the money spent on AI didn't bring us in this period a whole lot closer to producing what we'd now call artificial general intelligence, or for the large part, any particularly useful systems directly tackling the problems that people were trying to do, just the byproducts, like, for example, stimulating the development of time-sharing at MIT, or Lisp, or the invention of garbage collection, and so on, really present a pretty good return on investment. Then doing this kind of Kuhn normal science thing, looking at AI in the early computer science curriculum. So computer science is this collection of largely separate things, but to make a curriculum, you have to figure out which of these things are the core courses, which are the electives, what is it really important for students to know. I see that almost as a process of diplomatic negotiation where people from different camps get together and try and hash out some kind of compromise. I think the Turing Awards also work in the same kind of way, right? It must be like, hey, it's been a long time since we had a database winner. You know, maybe we should give one this year. So ACM and other computing societies worked together to put out a series of model curricula. The first one is in 1968. At that point, AI is an obscure course recommended for master's students and specialists in computing theory. And you can look over the next 20 years, it edges close to the mainstream. By 1978, Lisp is being recommended for coverage in a core course, and AI is a much more prominent elective. By 1988, everyone is supposed to get some AI. AI and robotics is recognized as one of the 9 core areas of computer science. Then in terms of how AI gets rid of neural nets, this is a really kind of famous story. I think people can probably, like most famous stories, I think it kind of captures something, but it may not have the causal explanation that is typically given. But Minsky himself, who'd begun as much more of a cybernetics, building like artificial connectionist brains kind of guy early on, with his colleague Seymour Papert at MIT, made a dramatic disavowal of neural nets. And you can argue about what they actually proved and what it really meant and so on, but it certainly captures the sense in which the elite AI community by the late 60s had turned decisively against connectionism and neural nets. Newell himself, linked lists, by the way, another contribution of early AI. Newell and Simon came up with that idea for their early system implemented at the RAND Corporation. So it's kind of interesting to see Newell's own view on how all this works. He saw it as a series of binary splits. One of them was splitting symbolic from continuous systems, AI from cybernetics, etc. Another one was problem solving versus recognition, which split AI from pattern recognition. They had famously the physical system hypothesis, which is basically something like Turing universality, and it claims that, as they put it, this is their Turing Award lecture, a physical symbol system has the necessary and sufficient means for general intelligent action. So in that sense, a computer programmed in Lisp, a universal Turing machine, and a thinking human could all be interchangeable. They're using different hardware, there's a different physical manifestation, but they're all fundamentally about system process, symbol processing. Aside, because the rest of the day is branded around symbolic and sub-symbolic, within that Newell way of seeing the world, it definitely makes sense to talk about symbolic and sub-symbolic, because the human brain, they believed, was a symbol processing machine, and therefore equivalent to a computer program. But underneath that, there were neurons, and you couldn't see the symbols directly in the neurons, so the neurons were sub-symbolic. If we don't believe that anymore, does it make sense to call connectionist approaches sub-symbolic if we don't believe that they're a way of implementing a higher level of symbol-based programming? And early textbooks were entirely symbolic. So looking at how AI shapes out, textbooks are of course important in shaping how people are taught, particularly outside those handful of elite institutions. The first 7 textbooks I could find, from 71 to 77, were all written by people with degrees from Stanford or MIT. The first really successful book was by Patrick Winston of MIT. He makes no mention whatsoever anywhere in that book, and this book was still used into the early 90s, of neural networks or connectionism, even though he actually was a specialist in computer vision and wanted computers to automatically learn and generalize concepts about shapes, but still completely symbolic. The other leading textbook of the era from Elaine Rich, 1983, gave it 2 sentences just to dismiss it, saying that no efforts to build learning programs starting with a random network had met with any degree of success and therefore would not be covered. So that is what mainstream AI thought about connectionism in the early 80s. Of course, neural nets didn't vanish, but they have a different branding. They're known as pattern recognition machine learning. They're tied to robotics. And they appear to move not just out of AI, but also out of computer science and into engineering disciplines. So preparing for this workshop made me think about that development between the idea of AI as all about symbol processing and levels of abstraction and so on in those terms, and about the development of computer science itself around these ideas of abstraction, the manipulation of symbols, etc., theoretical computer science as the moral an intellectual high ground of the discipline. So even though Newell saw AI as being isolated within computer science by some of these things, I think particularly the focus on symbols is something that helps it really resonate with this kind of intellectual approach that comes to be seen as the core of computer science. Couple quick concluding things on the broader project. So the book I've got here, it's a short book. It goes through, it's got this history. But what I find myself doing is basically splitting each chapter into a narrative section and a case study of a particular system. So AI, probably because the techniques they were using didn't really work and weren't generalizable, for decades, systems that seemed to kind of do something like Newell and Simon's GPS, Winograd Schrödlu, and so on, were appearing in textbooks as descriptions. So instead of generalizing away from the specific systems to the principles, the role of these like would-be paradigmatic tangible examples was really and unusually important in the development of AI, the way people were taught it. I also think the 90s are a really interesting shift that complicates some of this. So with the AI winter and the end of the expert system boom, it seems like it's a period where there's a lot of pluralism and a lot of different ideas being tried out. Russell and Norvig, as they put it in their now long-dominant textbook, Modern AI, they really jump on the work of Judea Pearl, which is probabilistic, but not big data. So it's not that we go straight from non-probabilistic, no big data, to neural nets, modern machine learning. Then even the arrival of big data in what we might broadly think of as AI through natural language processing is initially not with neural networks, it's with hidden Markov models and statistical parsing. And of course, neural nets become central to things in the 2010s, but they are, until very recently, seen mostly as being about classification, not being about generation. So in terms of that big picture mission for the workshop, we could kind of think through some of those more specific shifts within the big shift. Got my discussion here of AI as a brand. I'm not going to spend any time here. I know we want to be wrapping up, but it basically is what I found helpful in terms of thinking about why the promises made for AI and the threats of AI, the coming of superintelligence, the potential for job loss, the enormous importance, but also the threat. Those same predictions we hear now have been made in exactly the same terms since the 1950s. So we've got a continuity of the discourse around AI and profound discontinuities in the specific technologies branded as AI. And that's why I think the brand-like quality of AI is important to consider, even at the specific moment, whether something gets called AI or not. As I said, it's got more to do with funding, I think, than about any inherent connection to human cognition or technical content. And to wrap up with kind of this summary of the differences and continuities. So at the top, I've got the continuities, the hype, need the fastest computers, arbitrariness, loose connection to cognition. The discontinuities are profound. 20th century AI was mostly academic, government-funded, symbolic, about heuristic search, about humans formulating rules, about explicitly coded knowledge, and it was rarely applied outside the lab. AI today is essentially the opposite in all those respects. And my very last slide. So Google has this wonderful thing, the Ngram. You can feed in things on a large text corpus. You can see over time how the usage has been changing. So in the beginning, cybernetics is big. By the 70s, computer science is being discussed more often than cybernetics. AI has a big boom in the 80s, subsides, and only in the last 10 years actually regains the frequency with which AI was being discussed in this large text corpus in the 1980s. But look what happens with machine learning and AI, right? Poor computer science, which should be, it's a pretty important thing. You know, computer science is not doing badly in the modern world, but perhaps we see the impetus for the workshop here with, my goodness, look what happens there, right? Machine learning and AI greatly outstripping discussion. And AI is more likely to be abbreviated in general circumstances, right? So it's not even picking up when people talk about AI, only artificial intelligence. So the true incidence is probably really higher. I would say, though, okay, computer science is not being talked about quite as much as AI and machine learning. I'd say don't give up. If you compare how computer science is doing to how history is doing, you're still doing pretty well. I'd say, like, don't panic and just decide to give up on everything and throw your lot in with ChatGPT.
Thank you. Thank you, Tom. A remark, I think the slides are available afterwards. So there will be a PDF, so you can use this. You can have the slides afterward, download from the website. I welcome the two respondents from the Netherlands and from Italy, Lynda Hardman and Enrico Nardelli. I'm not going to introduce them. I just say that both are past presidents of Informatics Europe, which is the, let's say, the European Association of the computer science and not AI, but computer science departments and faculties. And I say you have the floors. You are now yours.
Okay, thank you very much.
10 minutes.
10 minutes. Is that 10 like 12 or 10 like 8?
Coffee break is a little bit postponed.
So I'd like to, of course, thank our speaker very much for this very high-level overview of what's happened in, I don't know, the past 70 years or something. I recognize very much of what you say, but I also miss a little bit the European contributions. I worked for a while in the artificial intelligence department at Edinburgh University at the beginning of the 80s. And this was very much a separate department from the computer science department. In fact, the computer science department was 20 minutes cycle ride away.
You have to go in the middle because otherwise you are not in the camera.
Oh, I need my computer.
Technical constraint.
Is it okay? Right. Oh yeah, it's a good idea.
He's an engine.
Yes. I want to solve issues.
Right. Where was I? So there I was working in the artificial intelligence department at Edinburgh University at the beginning of the 80s. And this department of AI was originated with a very small research group established in a flat at 4 Hope Park Square in 1963 by Donald Mickey, who was then a reader in surgical science. So again, reflecting what you were saying, you've got to come from somewhere for the science to exist already. And another point to note is this is exactly where I met my husband in 1984, so I have to thank AI. I also want to mention Alan Bundy, who did a huge amount of research in his career in AI, in particular in automated reasoning, in proof planning, with the use of meta-level reasoning to guide proof search. Again, this being the symbols in search that Thomas was mentioning. And again, I think the history of the AI department in Edinburgh, again, reflects what we've all heard, that the computer science department was somewhere far away. There was an epistemics department somewhere else, and they had some other things whose name I'm forgetting. And eventually, they all saw the light and put together a large new building now called the Informatics Forum in Edinburgh, where they put everyone together. And the other nice anecdote is they have all the people who think in the ivory tower at the top of the building and all the people doing the robots and the real engineering at the bottom, and there's a sort of symbolic statistical split in the building. Don't mention my name. So I think that also gives a similar flavor to these progressions through the years. I also noticed that the Turing Awards are perhaps very American-oriented. So if you have any friends you think should be ACM members or ACM fellows or ACM distinguished scientists, then nominate them. Even now we have, in Europe, much less of a representation in this international organization. But now I'm getting off topic. I also wanted to mention about the AI winter. Unfortunately, in the UK, we really did have an AI winter. We had somebody called James Lighthill, who was commissioned to write a report for the British Science Research Council to evaluate the academic research in AI in the UK. And basically his report said, well, they're not doing very well actually. They've promised all sorts of stuff and they're not delivering. I quote, "In no part of the field have the discoveries made so far produced the major impact that was promised." And this formed the basis for the decision by the British government to end support for AI research in most British universities, contributing to a real AI winter in Britain. So this was a real problem. And when I entered in the AI department at the beginning of the 80s, that had been felt. And after that, I think the Japanese started investing a lot of money in the 5th generation. And then the UK got, oh, wait a minute, if the Japanese are doing this, there was another report called the Alvey report, and then the British started pumping money into that. So that, again, increased the funding. You didn't mention Prolog at all, so much of my...
Prolog's in the book. I did
in the
my,
book.
programming in Prolog more than Lisp.
Right. So I recognized Lisp, and at Edinburgh I was also learned a bit of Prolog. For my sins, I had to write the manual for a DEC 10 Prolog interpreter, which I believe somebody found in the last 5 years and went, "Was that you, Lynda?" I'm going, yes, that was really me in the early 80s. So I think these other types of thinking, certainly I think Prolog programming, perhaps Lisp programming, are really specialist niches now. And I was at, let me get this right, the Tsinghua Computer Science Department celebrated its 60th birthday a few years ago. There's some debate as to whether the Tsinghua Computer Science was really 60 years old, but they managed to make themselves the oldest computer science department in China. And there we had a workshop with the deans of computer science departments around the world. And what was very much expressed is that they all agreed that teaching students machine learning, data processing was a very good idea. But they were very, very worried that the expertise was dwindling in the symbolic side. So again, that's another plea that I think we need both. And while in our field, machine learning is dominating, we need to think about what we want to do about it. So I hope that was a good 10 minutes. I'll pass on to... Oh, thank you very much.
Okay, thanks for the invitation to be here. And thanks to Thomas for this very nice presentation. And as Hannes revealed, I am an engineer, so I remember that I have chosen engineering as a field of study because I want certainty around me. So I want to do things precisely and not deal with the mess of human-related uncertainty. But then with years, I have become more and more nuanced, if I can use this expression, and I've started reflecting on the meaning of word, because too often the meaning of word is not shared, and if the meaning of word is not shared, then how can we understand? And actually, in the Thomas presentation, he spoke about the different paths that have followed computer science and artificial intelligence. And in Europe, we tend to use the term informatics to denote not what computer science is, but what maybe computing is. Because in our vision, informatics is encompassing all the sub-disciplines, while from what I can judge being here in Europe, in the US, computer science is seen as a discipline that is together with other disciplines like artificial intelligence or information retrieval and software engineering and so on. So first of all, I mean, it is important to understand what we are talking about. And maybe there will never be an agreement on what informatics is or computing is, but still we are doing it. Like some famous historian said, physics is what physicists do. So to me, informatics is what informaticians do. Now, for me, informatics is the mechanical manipulation of representations of facts that may exist in the real world or in some fictitious world. So I use the term fact in some loosey way, because in a fictitious world you cannot really speak about fact. But still, you have a mechanical manipulation of this. And by mechanical, I do not mean that you cannot use randomness. Indeed, you have randomized algorithms that use randomness. You have algorithms using statistics or probability. So that's not the meaning. The key point is that what is done by a machine, which is what, in some sense, Alan Turing wrote. I mean, what machine can automatically do. And following the challenge by Hilbert, whether it was possible to mechanically prove theorem, then Alan Turing worked on what machine can automatically do. So for me, informatics is what machine can automatically do. And in processing representation of facts, I don't use the word symbols because symbols carry a meaning, and the meaning is something that is bound to human beings, because are the human beings that are giving meaning to symbols. For us, some word, camera, for example, has a meaning that is shared among the Italian among the people speaking Italians as a room. For English-speaking people, camera is a video camera. So the meaning is something that is shared. But informatics manipulate representation automatically as a machine. And in doing this, it has been able to reach places or to reach points that only human beings have been able to do. I mean, first these machines have been doing mathematics, then have been doing symbolic representation. Now they are playing chess, playing Go, and defeating human beings. And now they are producing, I mean, wonderful representation of meaning generated by generative AI that, as you have reminded, somebody calls bullshit. And this is a problem because in this sense we are really coming out from the paradigm of informatics as being able to mechanically manipulate representation, because now with this production of things we are, to me, this is a personal evaluation, to me, when they produce something that is bullshit in this technical sense, then we are speaking really about defective software, because that's not what we wanted from a machine. For a machine, we want precise, exact consequences. That's what we have been working on. So in the end, what I want to say is that generative AI, because this is only part of AI, you have wonderfully pictured the entire history, and later today and tomorrow we will see other part. So generative AI has reached a lot of success, but we have to be carefully in using it for what it can produce to us. And what I'm a bit worried as a scientist is seeing all these emphasis on using it before we are really able to understand which advantage can give us. And we are seeing this in the world surrounding us. I remember we had a workshop in July last year where it seemed that generative AI was about to conquer the world. We are 15 months later. The business case is not yet there. So we have to see. You have showed this wonderful n-gram by Google, and usually when you look things afterwards, you can see something clearly. But if you cut the graph at some point, you cannot really foresee what will come out. And therefore, as a scientist, I think we have to continue studying this, but we have also to be careful in speaking to other people about what this discipline can do. Okay, I will stop here. I spoke too much.
I'm standing. Tom, you want to respond immediately, or do we pass over to the audience? One word, maybe. or two?
All right. Yeah, so on the AI winter, which is not even like the center of the talk, I think in the late 70s, there was an AI winter in Edinburgh and MIT. And because the people from those institutions have such an outsized role in terms of writing memoirs, giving keynotes, shaping the collective memory, that this, on the basis of very little data, has been generalized to a broadly based AI winter. At MIT previously, they were extremely friendly. I mean, people from MIT would take it in turns to go and be the director of the appropriate program at ARPA and give money to their friends, and then they'd come back and their friends would give money to them, and that stopped in the 70s, and they felt that. Edinburgh is certainly interesting as an alternative example for the development of AI. It gets mentioned mostly in the context of the Lighthill report and that cutting. I hope to be able to do a little bit more with it in the book. The challenge is that in a short book, and also the limited secondary historical literature of people writing about AI more broadly. But when I looked at the Ngram, when I looked at the membership of the ACM Special Interest Group, which soared for AI during the 70s, and when you look at things like, as I understand it, AI was institutionalized for the first time in Vienna in the 70s, and I suspect in many other places. I think if you look beyond MIT and Edinburgh, you get a different sense of what's going on in the 70s with AI.
Now the floor is yours. Who wants to? Francesco?
It works. Thank you for the talk. Thank you for the
Who are you?
I'm Francesco Ricci from the University of Bolzano. Thank you for the talk. Now, I want to go back to this paradigm shift now, because I think it's the topic of our workshop, and I think it's the important aspect that we have to understand. And so from my point of view, from the point of view of a person that have worked in AI for 40 years, the paradigm shift is very clear now. So the task is always problem solving in some sense now, but at the beginning we thought that it was fundamental to do knowledge representation and search, so to define what is the knowledge, define how the system should solve the problem. And then the task of the researcher was essentially to verify that what you have designed has really the properties that you were planning to put into the system. Now the situation is very different. Now the focus is on prediction and learning. So you are not supposed to, let's say, to embed the structure of the problem-solving algorithm, but the problem-solving algorithm is found through another problem-solving algorithm, and then you discover even some properties that you were not expecting the system could have. This is, in fact, I think, one of the most interesting aspects of even of large language model. We discovered that they are able to do something that we did not expect that they were able to do. This has created really a change in the way science is, especially computer science, is developing. And I think this is probably the most important, I think also most interesting aspect. That we are not just, let's say, designing our problem-solving solution, but we are learning from the machine. And so we are studying the machine as the proponent of the problem-solving solution.
Yeah, well, I'm Luke Steels from Brussels, let's say. Well, thank you, Thomas, for your great work. I think it's timely, and as you said, there is no history written, serious history written so far on computer science and on AI. So I think it's really fantastic that you're doing all this. But then, of course, we should start talking about, exactly the historical reality, because writing history is always interpreting the past. And there are many things to say, but maybe one is about the dichotomy between connectionism, neural networks, and the symbolic AI. Clearly, there are I think there are two different paradigms in a way, but certainly in the beginning, I don't think it's the division was so straight. The picture you showed of the Dartmouth, I mean, there's also Claude Shannon there in that picture. He was one of the organizers, and you know, he started in the 50s. His first papers also in information theory actually are the foundations, you could say, of machine learning, probabilistic, well, statistical machine learning and all that. So, and Solomonov was also there. So I think also Minsky, you know, as you pointed out, I mean, his thesis of 1951-52 was about neural networks, building one of the first SNARK machine. And the Perceptron book is really trying to build a theory of perceptrons. And so this also, together with Papert, you know, they proved the first theorems about perceptrons and all that. So I think if you look at the figures, or also somebody like Nielsen, who also wrote textbooks, who wrote one on neural networks also in the 60s. So I think this antagonism is actually quite recent, and you know, most people in earlier phases, you know, were doing both things or considering things for well, perceptrons and all that, mostly for, let's say, grounding symbols in visual data and things like that. So there is now indeed a paradigm shift, but I think we have to be careful in writing the history to make too many divisions, maybe. And also, I think there are other threads, you know, that also go, like, for example, taking a bio-inspired view, with maybe starting with John Holland, who was also connected to the Dartmouth. So the history of AI is more complex than having these two paradigms, and you know, one was winning and then the other one is losing. I think that's not correct, particularly because if you take a system like AlphaGo, let's say, I mean, it rests on search, it rests on heuristics, and all of those things that were developed in the 50s, 60s, when search and heuristics were dominating topics in AI. Yeah. Okay, well, there's a lot to say, but I think we should be careful. This is the message, actually, that we are not too rigid in terms of the categories that we use.
Yeah, so can I have my slides back for a moment? All right, so well, let's. So if we look at, I think I agree with that. Essentially, okay, where does the Dartmouth conference go? Up. Right. So at the beginning, very broad definition of AI, right? Which explicitly includes, as I pointed out, neuron nets, and it also includes computational complexity and etc. So the conception for the Dartmouth conference, very broad. So the narrowing, you have to look at how AI is institutionalized and turned into textbooks. Minsky himself, as I mentioned, had a kind of cybernetic, brain-building kind of mindset, and originally was involved also on what we would later think of as being connectionist. So my argument is that essentially during the course of the 1960s and into the early 1970s, that narrowing takes place that you see culminating in the widely used AI textbooks completely ignoring connectionism. In the case of the Perceptrons book, honestly, I think someone should just write a dissertation just on that. I'm not even equipped to understand the mathematical elements. I've seen readings of it that say that it's been completely misunderstood, but I also think it's inarguable that it passes into AI folklore as Minsky turned against neural nets and proved that they didn't work. Even if that is not actually a good reading of the book itself, I don't think anyone can argue that, say, by the mid to late 70s, people are like, they proved they can't do XORs, right? That's what that book gets compressed down to. So I think those textbooks from 77 and 83 are capturing peak symbolic dominance. It's also interesting, by the way, even Newell, with his series of binary splits to explain the partition of all this, he's got a little thing here in small print about the connectionism returning in robotics. So say even at Carnegie Mellon, yeah, it's Newell and Simon, but they're doing connectionism with machine vision for their projects in the 80s. So I agree that there's not just the two paradigms. And then in the context of my most recent communications of the ACM article, where I talk about this, another piece that I didn't put on the slide, but it's in the article, is this concept of artificial life and embodied intelligence. So I see after AI, with the flood of commercial money, gets in some way scoped down to expert systems, as far as at least investors are concerned in the 80s, the AI winter and the collapse of that boom leads to this conceptual opening up and a great rebroadening of the concept of what AI is all about, which under the flood of an even larger amount of money is in danger of being reduced at the moment to chatbots. So the whole history, I think, is these broadenings and contractings and shiftings. It's not just a simple two-paradigm story.
George?
Just a historical remark on terminology and the names used. Enrico mentioned informatics, or in English, it was mostly information technology that was used in the 80s and 90s. And there was a European program called ESPRIT, the European Strategic Program on Information Technologies. That program every year had to produce something called a work program that had sub-themes, research sub-themes. And these were defined by, let's say, researchers and, throughout Europe, many of them figuring on your Turing Award list. What I thought when I saw your engram was that if you think back to the work programs of the ESPRIT program that then morphed into the Information Society Technologies program, which still exists. If you look at the sub-themes of the annual work program, AI appears prominently, then drops, then goes up again, pretty much like your engram. And that would be an interesting, let's say, parallel study to make, because this was defined by the European researchers at the time.
Thank you, George. This was George Metakidis, who was the director of the ESPRIT program. Okay, so he knows. Our colleague Gerd Friedrich from, did you? Yeah.
Hello, yeah, so my name is Gerd Friedrich, Symbolic AI, Academia and Industry. Okay, so thank you for your talk. I think, although I'm also in the field for quite some time, I learned a lot, so thank you. This was really great. Just a comment, and maybe also a suggestion. I think since AI is also an engineering science, yeah, so the big question is how successful are this method, yeah, if it really comes to apply it to real world. And this means also how successful are, for example, methods, and also companies or concepts. And if you look at the history, then in the late 80s, we had these great companies where they are selling extremely expensive tools like knowledge craft and art and so on. And somehow it turned out that they were not really, the success was not sustainable. So it was somehow, these ideas got into object-oriented programming, or they ended up in constraint processing. Yeah? For example, iLog, which then was bought by IBM. But so in one sense, these symbolic methods were quite successful in the 90s in the applications, actually a particular area. But then we learned that actually we had some limits, yeah, in expressing things, yeah, just by logic or by knowledge representation, which then somehow gave room, yeah, to this machine learning or to this automated modeling. Yeah. So for example, in diagnosis, we had to learn, I mean, we had a great idea based on knowledge representation reasoning, yeah, on explicit knowledge representation, but it turned out there are so big limits, yeah, that we can't go further. And actually, if we would have been successful with this all specification approach, doing it by symbols, then there wouldn't have been any, I think, demand for something else. But actually this big success of machine learning and subsymbolic methods, I think, are induced by the limits we have as humans to use and apply KRR in specifying. Okay, and I think this is also the limit of applying. So this limit of applying something and gives room for great other ideas.
Thank you. I would like to pass over to.
Yes, thank you, Helga Novotny. I come from Science Technology Studies. I would like to draw attention to an elephant in the room. And the elephant was rather small in the beginning, but now it has become a huge elephant. It has also changed size, not only size, but also shape. And the elephant's name is funding. Researchers, as we all know, are opportunistic because they know they have to get funding from somewhere. And they are very clever in selling what they want to do in ways that appeal to what they think the funders expect. And this is the elephant. I would like to know more about what were the kind of relations to funding, what were the expectations on the part of governments in the beginning, the military in the beginning, but then it shifted to the large corporations that are now dominating in terms of funding. And as you know, the pattern has become very, very unequal. OECD countries in general, 1/3 comes from public funding, 2/3 from private, because R&D development is done in firms. But AI, 10% only come from public money and 90% from private. So I just wanted to know more about the change that went with the elephant in the room.
On the choreography we make now around here to answer this question, then we have questions over there, and then we stop, okay? Because you all want to have your coffee, but we postpone a little bit, okay? Because we started a little bit later.
Yes, so the funding question and also the application question. So expert systems in the 80s were the previous time where there were startups from AI, there was investor interest, there was a claim that this technology is being widely used in companies and will cause massive job losses and so on. And that was around the idea that while representing ordinary knowledge of the world is enormously challenging, that it turns out expert professional knowledge can be captured in a few hundred rules. This was coming particularly from Stanford, Ed Feigenbaum, another Turing Award winner. And he claims and continues to claim that within those specialized domains, systems that just have simple production rules and a small number of them within a narrow domain can outperform human experts. And if you look at the literature there, they really tried to prove this. So with the mice in diagnostic system, they tried clinical trials. They say doctors are very bad at this. This system is much better. It outperforms them. Here are our studies. We've proved it, and so on. And companies, there was the famous XCon/R1 system used at DEC to configure VAX mini computers, which was the example that everybody turned to look for, like, how is this technology being deployed? And the interesting thing is, when the AI brand, an expert system brand in particular, went out of fashion at the end of the 80s, there was convincing seeming evidence that this stuff actually worked and was saving companies money. So where did it all go? And I've asked people these questions. I asked Feigenbaum himself. I've asked people who worked in companies in this, who came forward and started emailing with me after some of this was published in CACM. And the best answer I have is, the stuff that was working didn't necessarily go away, but it was no longer in their interest to call it AI. That wouldn't get them respect in their companies, that wouldn't get them. So they started calling it rule-based systems and business logic. Rule-based approaches to computer security continued, etc. So in some companies, stuff that had previously been called expert systems continued, but because of this branding question, which applies to the academic world and the commercial world, it was just called something different. In fact, the original quote from 1984 warning about the potential for an AI winter finishes with, and everyone will start finding different names for what they do, which is exactly what happened when the bubble burst. And I'm confident it's what's going to happen in the next couple of years to the AI brand today, actually. But that's a different story. The funding, if you look at my list of example questions, of my example systems, what you see is it's only ChatGPT at the bottom, and Dragon Naturally Speaking, which was a privately funded development of work that had been carried out at IBM that built on work carried out at Carnegie Mellon that were privately funded. GPS was from the RAND Corporation, Military Industrial Complex, US Air Force. Shredlu was MIT, which is Project Mac, which is Military Industrial Complex, basically 2. Hearsay 2 is Carnegie Mellon, funded by DARPA. But there's this interesting shift in the 70s. Basically, Vietnam-era backlash, they wanted military funding to start being more specific and more relevant to military needs. So with this project, which was speech recognition, they came up with very specific deliverables, tests, timelines that the system had to meet. And while, Raj Reddy basically won a Turing Award for this. So it's seen as very important science, but it's also seen as disappointing by this new version of military funding, where the military is supposed to get specific deployable systems that meet benchmarks, versus the 60s heyday of ARPA funding, where they give out money with no particular demand for deliverables or accountability. MySyn was from the National Institutes of Health, which was smart. Feigenbaum, at that point, computer science is still pretty small. Doctors have got a lot of money, particularly at major medical center like Stanford. NIH had a lot of money. That project actually got NIH its first IBM System 360 mainframe and its first interactive computing capability for the Stanford Medical School. Psych is Feigenbaum having success convincing the American government that the Japanese are coming and are going to do to computing what they did to motorcycles and televisions. And it's a government-backed industrial consortium with hundreds of millions of dollars to try and do an AI symbolic moonshot and develop basically general intelligence, and it didn't. And AlexNet, the funding for that nicely captures this amazing run for neural nets after their decades in the wilderness in the early 2010s, because it's running on 2 commercial-grade graphics processing units in a graduate student's bedroom, and it's outperforming. And there's this string of stories. Cade Metz tells this story very nicely in Genius Makers, where suddenly there's a toolkit of technology that actually works. For the first time in the history of AI, surprises are coming on the upside. They're generalizing techniques, they're applying them, and the same thing happens very quickly with students of Jeff Hinton's at Google and Microsoft, deploying these GPU-based neural nets into big tech. And ever since then, AI has been pretty much the exclusive domain of big tech and big tech-backed startups.
Yeah, I would like just to say that I think there is another big elephant in the room, which is the very word intelligence. Because intelligence is human intelligence, and it was very clear in the Dartmouth proposal they were thinking to human intelligence. But in the human intelligence, there is not only the rational logic part on which we have seen so many successes. That's why when people outside our world, but also inside our world, our community, read or thinks to artificial intelligence, in their mind there is something like artificial heart. It does all the function of heart. It's simply made of metal and electricity. But this artificial intelligence does not do the function of human intelligence. It's only restricted to the rational and logic part. And this is, completely another species. It's not human beings. It will never be able to understand what human beings are. It should be called, but it's too late now, mechanical intelligence, because if I say that somebody behaves mechanically, then you really understand that it's behaving in some sense outside what you would expect from a human beings. That's why I think that the very word intelligence in itself is misleading. Unfortunately, we have to survive with this, but I have been reading some of the European legislation about artificial intelligence, have not been really able to distinguish what an AI system is from what a not AI system is. Because if you try to describe this in legalese term, in juridical term, then in the end you come to describing system that process representations to derive new representation, which is, I mean, what I call informatics in general. But we call them intelligence in normal speaking, and this triggers a lot of problems. So this is an elephant always to take into consideration.
We need to swap the camera. I'd like to go back to the funding that Helga mentioned. So I know in the Netherlands, where most of my experience is, where personally I feel that the research funding is insufficient, but that's easy to say because I'm a researcher in the Netherlands and it's always easy to say that. But about 12 years ago or so, one of my colleague professors at the University of Amsterdam realized that he could at least get some funding for some of the topics in computer science, which would be information retrieval, machine learning, so more AI type topics. And he went to a bunch of companies and talked to them and managed to extract, I think from each company, a couple of million euros, and that allowed the professors to set up a new member of staff for the department and about 5 PhD students. They called them labs. They've got a name, ECAI. I can't remember what the IC stands for, Centre for AI probably. And this gave a branding to the Netherlands, which allowed companies to fund more research. I would say the one good thing about this particular commercial research is that the deal was that all the work would be published. So there were various IP agreements all done on an individual basis. But the point was that it wouldn't just be consulting to the companies, there'd be publishable research going on. And that has been fairly, it's been going on for now maybe 7 years or so, maybe a bit longer, 8 years. And now we're getting back to the second round if the companies want to do that again, and some companies are interested. But again, it's sort of putting a bulge on the AI part of things on the whole computer science landscape. So, you know, the formal computer scientists are not getting this extra money. So I feel from an academic perspective, this is a bad idea. But, you know, if you're desperate, it's the only money there, then it's one way of doing it. So that wasn't a very optimistic note from the coffee, I'm sorry.
Anyway, thanks to you three. Thanks, Tom. Thanks, Lynda. Thanks, Enrico.